Mysterious Saturn is the second largest planet in the solar system in mass and size, and the sixth nearest planet in the distance to the Sun. Saturn is easily noticeable to the unaided eye in the night sky as a non-twinkling point of light. When observed through even a small telescope, the planet, encompassed by its magnificent rings, is arguably the most beautiful object in the solar system. Saturn's name comes from the Roman god of agriculture, compared with the Greek deity Cronus, one of the Titans and the father of Zeus, the Roman deity Jupiter. Saturn was also the slowest moving, as the most distant planet known to ancient observers. At a distance from the Sun that is 9.5 times as far as Earth's, Saturn takes approximately 29.5 Earth years to make one solar revolution. The Italian astronomer Galileo in 1610 was the first to observe Saturn with a telescope. Although he saw an abnormality in Saturn's appearance, the low resolution of his instrument did not allow him to discern the true nature of the planet's rings. Saturn occupies almost 60% of Jupiter's volume but has only about 1/3 of its mass, and the lowest mean density, about 70% that of water, of any acknowledged object in the solar system. Hypothetically, Saturn would float in an ocean large enough to hold it. Both Saturn and Jupiter relate to stars in that their bulk chemical composition is hydrogen-dominated. Also, as for Jupiter, the tremendous pressure in Saturn's deep interior maintains the hydrogen there in a fluid metallic state. However, Saturn's structure and evolutionary history differ significantly from its larger counterpart. Like the other giant or Jovian planets, Jupiter, Uranus, and Neptune, Saturn has extensive moons, natural satellites, and rings, which may provide clues to its origin and evolution to those of the solar system. Saturn's moon Titan is distinguished from all other moons in the solar system by a significant atmosphere, denser than any terrestrial planet except Venus. Saturn's most incredible advances in knowledge and most of the other planets have come from deep space probes. 4 spacecraft have visited the Saturnian system: Pioneer 11 in 1979, Voyagers 1 and 2 in the 2 years following, and after almost a quarter century, Cassini-Huygens, which arrived in 2004. The first 3 missions were short-term flybys, but Cassini went into orbit around Saturn for years of investigations, while its Huygens probe parachuted through the atmosphere of Titan and reached its surface, becoming the first spacecraft to land on a moon other than Earth's. The Cassini spacecraft traveled nearly 4 billion kilometers. It delivered an exploration probe to the surface of a toxic moon, spent some 20 Earth years in space. It has endured scientific procedures 9 years longer than initially planned. Cassini discovered flowing liquids where none were expected, phantasmagorical structures on a planet's icy rings, a weirdly breathing magnetosphere, and a possible abode of life in a tiny world with an incredible atmosphere. The Cassini spacecraft finally streaked into Saturn's heart, traveling over 124,000 kilometers per hour while streaming data directly to Earth before the searing heat tore it apart. Scientists organized their investigations based on past probes' findings as Cassini glided outward on a nearly 7-year transit to Saturn. Like the giant planet, their questions nest within one another, concentric rings. Does Saturn have a solid surface, or do its clouds thicken and down to specific densities? Perhaps creating exotic forms of matter, like metallic hydrogen. Is there a rocky core? Why are the rings so bright? How old are they? What is going on beneath the thick orange clouds of Titan, Saturn's largest moon? How are Saturn's moons and rings related? What will this giant planet tell us about the evolution of solar systems? At its distance of nearly 1.5 billion kilometers from the Sun, Saturn's orbit lasts 29.5 Earth years. Over the past Saturnian year, Earth has increased by 2.5 billion people. Average life expectancy rose from age 64 to almost 72 years. The Internet has exploded beyond comprehension. It now has almost 4 billion users. With half the world's population now on, in the time of Cassini, our world has been consumed with new ways of communicating, connecting, working, and living. Like Jupiter and most of the other planets, Saturn has a regular orbit. That is, its motion around the Sun is prograde, in the same direction that the Sun rotates, and has a minor eccentricity, non-circularity, and inclination to the ecliptic, the plane of Earth's orbit. However, unlike Jupiter, Saturn's rotational axis is tilted substantially, by 26.7%, to its orbital plane. The tilt gives Saturn seasons, as on Earth, but each lasts over 7 years. Another result is that Saturn's rings, which lie in the plane of its equator, are presented to observers on Earth at opening angles ranging from 0 degrees, edge on, to nearly 30 degrees. The view of Saturn's rings cycles over 30 years. Earth-based observers can see the ring's sunlit northern side for about 15 years, and then, in an analogous view, the sunlit southern side for the next 15 years. In the brief intervals when Earth crosses the ring plane, the rings are all but invisible. Saturn's rotation period was challenging to determine. Cloud motions in its massive upper atmosphere trace out a variety of periods, which are as short as about 10 hours 10 minutes near the equator, and increase with some oscillation to about 30 minutes longer at latitudes higher than 40 degrees. Scientists attempted to determine the rotation period of Saturn's deep interior from that of its magnetic field, which is presumed to be rooted in the planet's metallic hydrogen outer core. However, direct measurement of the field's rotation was difficult, because the field is highly symmetrical around the rotational axis. At the time of the Voyager encounters, radio outbursts from Saturn, apparently related to slight irregularities in the magnetic field, showed 10 hours 39.4 minutes. This value was taken to be the magnetic field rotation period. Measurements made 25 years later by the Cassini spacecraft indicated the field was rotating 6 to 7 minutes longer. It was believed that the solar wind handles some difference between these two measurements of the rotational period. The rotation period was accurately measured not until Cassini flew inside Saturn's rings on its final orbits. By relating waves observed in the rings to slight variations in Saturn's gravitational field, the planet's rotation period was determined to be 10 hours 33 minutes 38 seconds. The time differences between the rotation periods of Saturn's clouds and its interior have been used to estimate wind velocities. Because the 4 giant planets have no solid surface in their outer layers, by convention, the values for the radius and gravity of these planets are calculated at the level at which 1 bar of atmospheric pressure is exerted. By this measure, Saturn's equatorial diameter is 120,536 kilometers, 74,898 miles. In comparison, its polar diameter is only 108,728 kilometers, 67,560 miles, or 10% smaller, which makes Saturn the most oblate, flattened at the poles, of all the planets in the solar system. Its oblate shape is apparent even in a small telescope. Even though Saturn rotates slightly slower than Jupiter, it is more oblate because its rotational acceleration cancels a more significant fraction of the planet's gravity at the equator. The planet's low gravity, 896 centimeters, 29.4 feet per second squared, is only 74% of its polar gravity. Saturn is 95 times as massive as Earth, but occupies a volume 766 times greater. Its mean density of 0.69 grams per cubic centimeter is thus only some 12% of Earth's. Saturn's equatorial escape velocity, the velocity needed for an object, which includes individual atoms and molecules, to escape the planet's gravitational attraction at the equator without having to be further speeded up, is nearly 36 kilometers per second, 80,000 miles per hour at the 1 bar level, compared with 11.2 kilometers per second, 25,000 miles per hour for Earth. This high value shows that there has been no significant loss of atmosphere from Saturn since its formation. Cassini's entire exploration lasted less than half a Saturnian year, from late winter through early summer. The Saturn system lies 9.5 astronomical units from the Sun, nearly 10 times farther than Earth. The planet spins fast, rotating its axis once every 10.5 hours. The grand clockwork speeds along at 34,900 kilometers every hour. A year on Saturn lasts only 11,000 Earth days. It is about 24,500 Saturn days. Made up mostly of hydrogen and helium, Saturn is the minor dense planet of all the planets. It has often been reported that Saturn would float if you could find a bathtub big enough. That is not entirely accurate, and its density is much lower than liquid water in Earth's oceans. Moreover, it is significant that you could pour nearly 800 piles of Earth into the volume of Saturn. The Saturn Mission was officially named Cassini-Huygens, honoring two remarkable men of 17th century science, the French-Italian Giovanni Domenico Cassini and Dutch Christian Huygens. They were crucial players in the scientific revolution. They collaborated and competed throughout their lives, transforming astrology into astrophysics. Cassini built and refined long-tube refractor telescopes as director of the Paris Observatory. However, Huygens removed the cumbersome tube, inventing the so-called air telescope. Furthermore, it is a well-engineered eyepiece. In 1665, Cassini co-discovered Jupiter's Great Red Spot. Furthermore, used it to time the giant planet's rotation. Huygens applied Galileo's ideas, invented the pendulum clock and developed the balance. Spring watches, both critical inventions in studying space-time. Though Huygens had seen them first, Cassini published maps of surface markings on Mars. Furthermore, Huygens pegged the length of the Martian day at 24.5 hours, just 6 minutes shy of the correct figure we use today. By getting parallax observations of Mars, Cassini was the first to estimate the size of our solar system. Furthermore, Cassini used Galileo's measuring time by watching the eclipses of Jupiter's moons to lie outlines of longitude on Earth. Endeavoring to perfect the geometry of optical lenses, Huygens developed the wave theory of light, setting today's quantum mechanics. We had known Saturn as the ringed planet since 1655, when Christian Huygens explained what Galileo had seen 45 years earlier. Cassini explained the so-called zodiacal light seen by astronomers as the reflection of sunlight of dust in the planet of the solar system toward the end of his life. Huygens determined liquid water to be a critical factor in searching for extraterrestrial life. A quest is now undertaken by the Cassini spacecraft and its Huygens probe. If you were standing on most of Saturn's moons, you would have difficulty seeing the rings, because most moons ride in the ring plane. You can only view them edge-on. Viewed from Earth, Saturn has an overall hazy yellow-brown appearance. The surface seen through telescopes and in spacecraft images is a complex of cloud layers decorated by many small-scale features, such as red, brown, and white spots, bands, eddies, and vortices that vary over a reasonably short time. In this way, Saturn resembles a blander and less active Jupiter. Storms similar in impressiveness to this great white spot, so named in analogy with Jupiter's great red spot, have been observed at about 30-year intervals dating back to the late 19th century. A spectacular exception occurred during September to November 1990, when an extensive light-colored storm system appeared near the equator, expanded to a size exceeding 20,000 kilometers, 12,400 miles, and eventually spread around the equator before fading. This is close to Saturn's orbital period of 29.4 years, suggesting that these storms are seasonal phenomena. Saturn, showing an Earth-sized storm, light-colored patch, in its northern equatorial region in a composite image made from observations with the Hubble Space Telescope on December 1, 1994, over 2 months after the storm's discovery. Large storms are relatively rare on Saturn, which has a less active atmosphere than Jupiter. Saturn's atmosphere is composed mainly of molecular hydrogen and helium. The same relative abundance of the two molecules is unknown, since helium must be measured indirectly. Currently, the best estimate is that the planet's atmosphere is 18 to 25% helium by mass. The rest is molecular hydrogen and about 2% of other molecules. Helium is less abundant relative to hydrogen than the Sun's composition. If hydrogen, helium, and other elements were present in the same proportion as in the Sun's atmosphere, Saturn's atmosphere would be about 71% hydrogen and 28% helium by mass. According to some theories, helium may have settled out of Saturn's outer layers. Other major molecules observed in Saturn's atmosphere are methane and ammonia, 2 to 7 times more abundant relative to hydrogen than the Sun. Hydrogen sulfide and water are also suspected in the more profound atmosphere, but have not yet been detected. Minor molecules that have been detected spectroscopically from Earth include phosphine, carbon monoxide, and germane. In chemical equilibrium, such molecules would not be present in detectable amounts in a hydrogen-rich atmosphere. They may be products of high pressure and temperature reactions in Saturn's deep atmosphere, well below the observable clouds, transported to visible atmospheric regions by convective motions. Several other non-equilibrium hydrocarbons are observed in Saturn's stratosphere: acetylene, ethane, and possibly propane and methyl acetylene. All the latter may be produced by photochemical effects from solar ultraviolet radiation, or, at higher latitudes, by energetic electrons precipitating from Saturn's radiation belts. Saturn's visible layer of clouds is formed from molecules of minor compounds that condense in the hydrogen-rich atmosphere. Although particles formed from photochemical reactions are seen suspended high in the atmosphere at levels corresponding to 20 to 70 millibars, the main clouds begin at a level where the pressure exceeds 400 millibars, with the highest cloud deck thought to be formed of solid ammonia crystals. The base of the ammonia cloud deck is predicted to occur at a depth corresponding to about 1.7 bars, where the ammonia crystals dissolve into the hydrogen gas and disappear abruptly. Nearly all information about deeper cloud layers has been obtained indirectly by constructing chemical models of the behavior of compounds expected to be present in a gas of near-solar composition following the temperature-pressure profile of Saturn's atmosphere. The bases of successively deeper cloud layers occur at 4.7 bars, ammonium hydrosulfide crystals, and 10.9 bars, water ice crystals with aqueous ammonia droplets. Although all the clouds mentioned above would be colorless in the pure state, the actual clouds of Saturn display various shades of yellow, brown, and red. Chemical impurities produce these colors, perhaps as the photochemical products rain down on the clouds from above. Phosphorus-containing molecules are also candidate colorants. From the right, watch tiny Prometheus, 86 kilometers across, pass behind big that this 1,062 kilometers wide. Little Pandora scoots through from left to right. Here, medium-sized Mimes traveling 14 kilometers per second glides in front of the larger Rhea at 8 kilometers per second. When Cassini launched, 18 moons orbited Saturn, and Cassini's mission suspected 13 more. Astronomers confirmed 53, with another 9 marked as conditional. Only one of them is enormous, hence the name Titan. In 1655, Christian Huygens was the first to observe Titan. Giovanni Domenico Cassini discerned Iapetus in 1671, Rhea in 1673, Dione in 1617, Tethys in 1685. The sky-watching siblings William and Caroline Herschel found Mimas and Enceladus in 1789. In 1848, Hyperion was spotted by the father-son team of William and George Bond in the US and William Castle in the UK. Phoebe was the first moon to be discovered through photography by the American astronomer William Henry Pickering in 1898. Some of Saturn's moons are probably captured objects, particularly those in retrograde orbits, like Phoebe, and they orbit backward in the opposite direction from the rotation of the planet. Each Saturnian moon is unique in the majestic planet's elaborate necklace. Before Cassini, no one suspected and sold it to be anything other than a dead ball of rock and ice. Scientific sleuthing led to a remarkable discovery. Enceladus is about 480 kilometers in diameter. It would fit neatly between Los Angeles and San Francisco. The first good close-up taken by Voyager 2 in 1981 showed the globe was remarkably bright and free of craters. Enceladus is by far the whitest body in the solar system. The first hints of a more complex story come from Cassini's magnetometer. The moon's magnetic signature looks more like a comet. Field lines are bent around Enceladus' south pole. A closer flyby shows that the southern polar region has been recently resurfaced. Cassini's infrared spectrometer shows the area is about 100 degrees warmer than the rest of the moon. Furthermore, that heat signature aligns with 4 prominent tiger stripes appearing across the moon's southern terrain. They turn out to be fissures, cracks in the icy surface. Each is about 150 kilometers long and 1 kilometer wide. Scientists name Alexandria, Cairo, Baghdad, and Damascus. Cassini eventually locates over 100 of these geysers. Mission planners arrange more flybys, and in October 2015 navigate within 50 kilometers of Enceladus' south pole and right through the jets, giving the instruments a chance to taste and smell them. Ice shoots out into space from each jet of water vapor and water. It is mostly water ice. There are also some ammonia, methane, and carbon dioxide, key compounds associated with life, and hydrogen gas, which microbes, if there are any, could use as a source of energy. Like frozen sea spray, some salty particles are flavored with sodium and potassium. The science team imagines a large subsurface ocean lies beneath the icy crust as it sloshes around carbon dioxide, making it fizzy like bottled soda. When it finds a path to lower pressure through the cracks of the tiger stripes, it sprays out into space like champagne when the cork pops. Most of these salty water particles fall back to the ground as snow decorates and repairs the surface of Enceladus. Some escape. Enceladus is weak in gravity, so Enceladus rides a misty ring of its creation. If the moon shuts off its water jets, this E-ring will dissipate entirely within a few hundred years. Tracking and modeling icy tendrils made by interacting geyser jets lets researchers calculate how much mass Enceladus is pumping into Saturn's rings. Furthermore, sell it as orbits in resonance with the moon Dione. Their dance is thought to heat their rocky cores. It is likely that Dione too has a subsurface ocean. Dione's enormous crater, Creusa, paints bright rays at least 500 kilometers across the moon's surface, giving researchers a marker of geologic time. Craters younger than Creusa disturb the rays, older ones underlie them. Water is pulled down into the hot cores of these moons, re-emerging as steam through the sea floor. We know this because Cassini has detected tiny silicate particles that can only form in boiling water. In Earth's oceans, hydrothermal vents are called black smokers, and white smokers are oases for life. The churning hot water provides energy and sets nutrient particles swirling around. Is the same thing happening beneath the ice crystal crusts of Saturn's snow globe moons? To find out, future missions must look for amino acids, fatty acids, long carbon chain molecules, and perhaps microorganisms hitchhiking on the ice crystals blasted far from the undersurface ocean depths. Many astrobiologists are fascinated by Titan because it is freezing, about -180 Celsius. Titan is almost indeed not related to life on Earth. Titan is about the same diameter and mass as Mercury, and Titan's surface gravity is about the same as Earth's moon. Unlike Mercury or the Moon, Titan has a thick atmosphere, thicker than Earth's. Furthermore, scientists do not yet know why. It is the second largest moon of the entire solar system at 5,150 kilometers in diameter. Only Jupiter's Ganymede is wider. Titan is so much larger than the rest of Saturn's moons, it may have formed from the collision of several of its siblings. Cassini will have flown by Titan 127 times by the mission's end. Each pass gives the craft a gravitational acceleration equivalent to almost 1,000 kilos of extra fuel. When the two Voyagers sailed past in 1980 and 1981, they saw only this orange smog and shrouded globe. American and European scientists were so intrigued that they began sketching out what would become the Cassini-Huygens mission. 23 years later, an international team commanded the release of Huygens' probe to land on Titan on January 14, 2005. The European built the Huygens probe, which broke into Titan's atmosphere with its heat shield, deployed a parachute, and floated down for over 2.5 hours through a nitrogen-laden atmosphere. Its camera revealed an eerie landscape. Huygens landed softly in a slushy bank of frozen methane. Huygens continued transmitting data for another half hour after landing along the shoreline of a hydrocarbon lake, sending back images of rounded pebbles probably made of hard frozen water ice. Humanity has placed its imprint on yet another world. The flowing liquid on Titan is methane, which acts there as water does on Earth between Titan's temperatures. Methane can exist in all three states: solid, liquid, and gas. It is not impossible that life could develop on this moon, feeding on the constant hydrocarbons rain. A true second Genesis was utterly separate from our earthly tree of life. Since Voyager first glimpsed Titan, researchers have speculated that liquid oceans grace its surface. Dense orange smog has withheld the truth. This haze collects when the sun's ultraviolet light breaks up methane in the high atmosphere, forming long molecular chains that grow large enough to fall from the sky. These methane byproducts form snowdrifts into a massive network of dunes around Titan's equator. Cassini's camera was outfitted with near-infrared filters to peer through the orange fog to verify bodies of liquid. Images come back of relatively flat areas, but are they truly oceans? Or perhaps just methane slush or thick tar? The answer comes from Cassini's visible infrared mapping spectrometer. It catches a specular reflection, a bright spot of sunlight bouncing off a liquid surface with Cassini's radar. Flat surfaces, lakes, and seas appear dark unless waves ruffle them. Titan has oceans, ponds, liquid hydrocarbons, ethane, methane, and propane pools. Strangely, they form primarily in Titan's northern hemisphere, near the pole. Saturn's eccentric orbit is to blame. Northern summer is warmer than southern summer on Saturn, but because Titan is tipped, its southern summer is more severe, so all the southern liquid methane evaporates and rains out in the north. Over time, the entire system flips. In 15,000 years, Titan's lakes will all be in the southern hemisphere. This one is named Ligeia Mare and is more significant than Lake Superior on Earth. It is probably 150 meters deep in spots. Mysterious frothy islands appear bubbling up from under the surface. Titan holds a store of hydrocarbons about 10 times larger than all Earth's petroleum and natural gas reserves combined. Hovering 300 kilometers over Titan's south pole, a huge, persistent toxic cloud of frozen hydrogen cyanide rotates ominously. This vortex seems to develop when Titan's southern hemisphere enters its autumn season. Titan thrusts methane into space at an alarming rate. The atmospheric supply cannot last longer than about 20 million years. Something must replenish it. But what? Cassini's radar spots the answer. Mountains, some up to 1 kilometer tall. These may be cryovolcanoes. Some could be active today, spewing methane from within the Moon. Even after Cassini-Huygens, we still do not know how old Titan is, or where it came from. Cassini's radio science tools showed Titan's whole body flexing in response to Saturn's gravity that makes it warm enough inside to melt ice. Unlike the subsurface oceans of Enceladus with its rocky ocean floors, Titan's ocean is probably sandwiched between layers of water ice. So if there is an underground marine layer, it may be sealed off from the hot chemistry of geothermal vents and any chance of nurturing life forms. Alternatively, how long it has had a vibrant atmosphere. Clues point to a cataclysmic event in the Saturn system, perhaps 100 million years ago, that created Titan from smaller bodies or energized a barren, frozen Titan into an active system, possibly like the primitive Earth. To find out, we must go back, float longer through the haze, sail of the hydrocarbon seas. Furthermore, soar through the nitrogen skies of Titan. To Galileo in 1610, the ringed planet appeared as 3 stars, with 2 small ones touching one large, prompting Galileo to declare that Saturn must have ears. In 1655, Christian Huygens unmasked the apparition as a flat ring circling a spherical planet, using advanced optics. 20 years later, Giovanni Domenico Cassini discerned it was not one ring, but several gaps between them. The widest gap was later named the Cassini division. We now know that it is 4,800 kilometers wide and far from empty. In 1859, Scottish mathematician James Clerk Maxwell showed that the rings were not solid disks, but composed of smaller granules. Each tiny flick, pebble and boulder revolves around the planet in its orbit, jockeying for position among trillions of others. Though all fly several kilometers per second, they gently jostle one another. In their discovery order, the concentric rings are given letters and A through G. In their discovery order, material writing close into Saturn's cloud tops in the D ring whips around Saturn in about 4 hours, but particles in the distant F ring take at least 4 times longer. It was not until Cassini's inspection that we learned how flat the rings are incredible, and they are only 10 meters thick on average. From top to bottom, only about as tall as a 3-story building. These rings are 30 million times wider than they are high. Furthermore, ring material can ripple up and down, crafting temporary corrugations. Many intricate wave patterns can be seen across the broad ring plane. A specific gravitational resonance conjures each one with a Saturnian moon. Through the fundamental physics of the ring, the system is simple. It is primarily the product of gravity and collisions. The intricate structure of the rings is hard to model, even after 13 years of Cassini observations mathematically. The pressure of sunlight and forces from Saturn's magnetic field can push or pull smaller, less massive ring particles around. The mission team flies a series of special orbits that put the rings between Cassini and Earth. Researchers build up a color map of particle sizes by beaming radio signals of 3 different wavelengths through the ring material. Red areas hold more big particles. Blue regions contain mostly smaller grains. Radio waves shown in the bottom half of this image reveal a more refined structure than photos taken in visible light. Most particles are small, from tiny crystals more minor than a dust grain to pebble-sized. Less common are rocks, ice, and large boulders up to the size of houses. A few are the size of mountains. Moons forming or falling apart. Grabbing an average-sized ring particle would feel like closing your hand around a thick layer of icy whipped cream to find a glob of solid ice cream deep inside. The packing of particles varies between rings. Very little light breaks through the B ring of crowded snowballs. An astronaut would have to dig her way through it. The ring is less congested. The ring is very diffuse, like fog or smoke. The Cassini mission confirms the rings are almost pure water ice, but tiny quantities of simple organic compounds tint and shade them. The astronomer Carl Sagan called these colorful chemicals called tholins, which is Greek for muddy. Crossing Saturn's dark side, Cassini's camera picks up the actual colors and intricate complexity of the ring plane's variations. Subtle gravitational effects fashioned by the many moons sculpt the ring material. Small moons, this one's named an orbit within the rings, they seem to sweep clear their lanes of travel. The moon Mimas gravitationally combing the ring's particles causes the large Cassini division. Other rings are herded into form by so-called shepherd moons like Prometheus and Pandora. Tiny Daphnis pushes a wave of ring material like the bow wave of a boat on a lake just 8 kilometers across. Daphnis bob up and down like a merry-go-round horse, gravitationally pulling particles into dome-like mounds 3 kilometers tall. It has ploughed a 35-kilometer-wide furrow in the Keeler division ring field. The larger Pan forges the 325-kilometer inky gap in Saturn is a ring, giving it a wavy edge. Pan's gravity inspires a spiral wake of particles. Researchers predicted Pan's existence in the late 19th century, based on that gap, long before it was first seen. No one expected Pan's remarkable shape. Furthermore, it is not unique. The slightly wider moon Atlas has a similar structure. Both wear skirts of gravitationally attracted icy crystals. Certain small satellites on eccentric orbits repeatedly crashed through the F-ring, leaving behind sets of disruptive splashes as evidence of their passing. Other minuscule moonlets too small to be seen fashioned propeller-shaped resonant waves in the snowy rings falling around Saturn. The ever-strengthened complexity of these ring circles moves like a musical score playing in silence. Space. Once every 14 years, the ring plane lies precisely edge of the Sun. Cassini was present for one such equinox. The sunlight on the rings has been switched off, and they cast no shadows on Saturn. They are only visible because Saturn reflects some light on them here, digitally multiplied many times. Only the F-ring, slightly tilted from the others, catches the sunlight. Because the rings are so thin, any tall structure within them throws its shadow onto the ring plane. Thus, in the outermost edge of the B-ring, a surprise appears that hundreds of long shadows mark a field of icy spikes. Geometry dictates that these points must range up to a kilometer. Like icebergs growing in a sea of mostly space, these thorn-like clumps may be molded by the invisible fingers of a gravitational resonance with one moon. Alternatively, they may be drawn out by static electricity inspired by Saturn's magnetic field. Some of Saturn's rings are constantly morphing, and others are stoically consistent year after year. How old are these bright, icy rings? In the last 100 million years, they may have formed when icy moons or comets collided or were torn apart by Saturn's gravity. Alternatively, they might be as old as Saturn, the leftover debris of the solar system's birth. Cassini may yet find the proper answer. Looking down at Saturn's the North Pole, Cassini views the globe's jet stream. Some residence of wind energies banks the stream into a six-sided shape, a hexagon. Occasional storms bump an eastward flowing shallow jet stream, and the jet reacts by settling into the most stable geometric shape, 6 roughly equal sides. This polar monsoon is about 32,000 kilometers wide. You could fit 2.5 piles of Earth into it. Its winds blow faster the closer they get to the pole, up to 540 kilometers per hour. So, why destroy Cassini in a ball of atmospheric fire? The international scientific community has agreed to avoid any possibility of contaminating Saturn's moons, especially Enceladus and Titan. Cassini is warm inside, essentially room temperature. Any microbes that found their way in during assembly could have easily survived. Furthermore, Cassini's RTG will remain hot for many decades if she may crash on Enceladus accidentally, and Cassini might quickly melt her way down through the ice into the underground ocean. In 2009, studies had shown Cassini had enough fuel to go beyond Saturn to explore the ice giants Uranus or Neptune. She could have been sent back to Jupiter. We are outward to visit a population of comet-like asteroids known as the Centaurs. However, Cassini would have to die here to get all the science possible from the Saturn system. That led trajectory designers at JPL to develop a jewel of orbital dynamics, the Solstice Mission. The plan optimizes repeated flybys of Titan. The route features high orbits to look at the poles and the rings, long loops to map the planet's magnetic fields, flattened equatorial orbits to check out moons. Furthermore, ending at the peak of northern summer, look to mirror Cassini's arrival in southern summer. Between the two, scientists can infer the complete cycle of Saturn's seasons. The science based is on Cassini's data. It will go on for decades. Nudging Cassini's speed by just 8 meters per second is enough to begin her death spiral. A final pass, 100,000 kilometers from Titan, seals Cassini's fate, which will make repeated dives between the innermost ring material and the roiling atmosphere. Maneuvers were far too dangerous to contemplate when Cassini was designed, beaming science data directly to Earth until the very end. A consequence of Saturn's sizable axial tilt is that the rings cast dark shadows onto the winter hemisphere, further reducing the dim winter sunlight. During winter, Cassini images of bright swathes of the northern hemisphere revealed a clear blue atmosphere, which perhaps was a consequence of the comparative lack of photochemical haze production in the ring's shadows. Even at the extremely high pressures found deeper in Saturn's atmosphere, the minimum atmospheric temperature of 82 Kelvin is too high for molecular hydrogen to exist as a gas and a liquid together in equilibrium. Thus, there is no distinct boundary between the shallow visible atmosphere, where the hydrogen behaves predominantly as a gas, and the more profound atmosphere resembles a liquid. Unlike the case for Earth, Saturn's troposphere does not end at a solid surface. However, it extends tens of thousands of kilometers below the visible clouds, becoming steadily denser and warmer, eventually reaching temperatures of thousands of kelvins and pressures over 1 million bars. Saturn's atmospheric circulation is dominated by the zonal east-west flow, like the other giant planets. This manifests itself as a pattern of lighter and darker cloud bands similar to Jupiter's, although Saturn's bands are more subtly colored and are wider near the equator. The features in the cloud tops have such low contrast that they are best studied by spacecraft. Since Saturn lacks a surface, its winds must be measured relative to some other frame of reference. As with Jupiter, the winds are measured concerning the rotation of Saturn's magnetic field. Virtually all Saturn's atmospheric flows are to the east, toward rotation in this frame. The equatorial zone, at latitudes below 20 degrees, shows an active eastward flow having a maximum velocity close to 470 meters per second, 1,700 kilometers, 1,050 miles per hour, but with periods when the velocity is 200 meters per second, 700 kilometers, 450 miles per hour slower. This feature is analogous to Jupiter, but extends twice as wide in latitude and moves 4 times faster. The highest winds on Earth occur in tropical cyclones, where, in extreme cases, sustained velocities may exceed 67 meters per second, 240 kilometers, 150 miles per hour. The zonal flows are remarkably symmetrical about Saturn's equator. Each one at a northern latitude usually has a counterpart at a similar southern latitude. Strong eastward flows, those having eastward relative velocities over 100 meters per second, 360 kilometers, 225 miles per hour, are seen at 46 degrees north and south and at about 60 degrees north and west. Westward flows, which are nearly stationary in the magnetic field's frame of reference, are seen at 40 degrees, 55 degrees, and 70 degrees north and south. After the Voyager encounters, improvements in Earth-based instrumentation allowed observations of Saturn's clouds at a distance. Made over many years, these agreed with the detailed Voyager observations of the zonal flows, and thus corroborated their stability. The mechanism by which the flow of the jets is maintained in the presence of atmospheric friction is unknown. Strong hurricane-like cyclonic vortices are found within about 11 degrees of Saturn's north and south poles. The warm eye of the vortex at the South Pole has a diameter of 2,000 kilometers, 1,200 miles, and is ringed by clouds towering 50 to 70 kilometers, 30 to 40 miles above the polar clouds. Tropical cyclones in Earth's southern hemisphere also have warm central eyes, flow clockwise, and are ringed by high clouds, all at a much smaller scale. Unlike hurricanes on Earth, there is no ocean below Saturn's vortices. The first jet to the south of the northern vortex at 75 degrees north follows a hexagonal pattern around the planet. Cloud features move around the hexagon counterclockwise at about 100 meters per second, 360 kilometers or 220 miles per hour. Similar angular patterns have been observed in buckets of spinning fluids and probably arise from interacting waves. The hexagonal wave is stable, and it developed at this latitude in Saturn's atmosphere is not yet understood. A wide variety of smaller-scale features has also been observed in the atmosphere. Particularly striking are about 24 similarly sized, 1,500 kilometers, 930 miles in diameter cloud clearings spaced nearly uniformly across 100 degrees of longitude near 33.5 degrees north. In infrared images of Saturn's thermal emission, these clearings appear as a bright string of pearls stretching across the planet. In the southern hemisphere, short-wave radio emissions from lightning storms, hundreds of times more intense than those on Earth, and lasting weeks to months, were frequently detected by Cassini at 35 degrees south. The thunderstorm centers are associated with thick, light-colored cloud features produced by strong convective motions driven by water vapor. The latitudes of the cloud clearings in the north and the lightning storms in the south are zones of fast westward winds, traveling opposite to most of the other zonal flows on the planet. Theoretical modeling of a deep convecting fluid planet such as Saturn shows differential rotation occurs along cylinders aligned about the planet's mean rotation axis. The general north-south symmetry suggests that the zonal flows may be connected in some fashion deep within the interior. Thus, Saturn's atmosphere may be built of a series of coaxial cylinders aligned north-south, each rotating at a special rate, giving rise to the zonal jets seen at the surface. These cylindrical layers do not start rotating together until a depth of about 9,000 kilometers, 5,600 miles. Much deeper than the point at which differential rotation stops on Jupiter. Saturn's magnetic field resembles that of a simple dipole or bar magnet. Its north-south axis aligned to within 1 degree of Saturn's rotation axis, with the center of the magnetic dipole at the center of the planet. Like Jupiter's, the field's polarity is opposite that of Earth's present field, i.e., the field lines emerge in Saturn's northern hemisphere and re-enter the planet in the southern hemisphere. See Earth, the geomagnetic field and magnetosphere. On Saturn, any ordinary magnetic compass would point south. Saturn's field deviates measurably from a simple dipole field. This manifests itself both in a north-south asymmetry and in a slightly higher polar surface field than is predicted by a pure dipole model. At Saturn's 1-bar surface level, the maximum polar field is 0.8 Gauss north and 0.7 Gauss south, very similar to Earth's polar surface field, while the equatorial field is 0.2 Gauss compared with 0.3 Gausses at Earth's surface. Jupiter's equatorial field, at 4.3 Gausses, is over 20 times stronger than Saturn's. If one represents Saturn's magnetic field as produced by a simple current loop with a specified magnetic moment, see magnetic dipole, then that magnetic moment is about 600 times Earth's, whereas Jupiter's magnetic moment is 20,000 times Earth's. Saturn's magnetic field is generated by the fluid motions in the electrically conducting portion of the planet's interior. This region, in which hydrogen exists in a fluid metallic state around a central rocky core, comprises the inner half of the planet. Compared with Jupiter, less of Saturn's mass and volume comprises this conducting metallic fluid, partly explaining why Saturn's magnetic field is much weaker. Jupiter's interior is also hotter, so the fluid motions in its interior may be more vigorous, possibly contributing even further to the differences in the field strengths. Like the magnetospheres of Earth and Jupiter, Saturn's inner magnetosphere traps a stable population of highly energetic charged particles, primarily protons, traveling in spiral paths along magnetic field lines. These particles form belts around Saturn, similar to the Van Allen belts of Earth. Unlike the cases of Earth and Jupiter, Saturn's charged particle population is substantially depleted by the absorption of the particles onto the surfaces of solid bodies that orbit within the field lines. Voyager data showed that holes exist in the particle populations on field lines intersecting the rings and moons' orbits within the magnetosphere. Saturn's moons Titan and Hyperion orbit at distances close to the magnetosphere's minimum dimensions, and they occasionally cross the magnetopores and travel outside Saturn's magnetosphere. Energetic charged particles trapped in Saturn's outer magnetosphere collide with neutral atoms in Titan's upper atmosphere and energize them, eroding the atmosphere. The Cassini orbiter observed a halo of such energetic atoms. Saturn possesses ultraviolet auroras produced by the impact of energetic particles from the magnetosphere onto atomic and molecular hydrogen in Saturn's polar atmosphere. Ultraviolet images of Saturn taken by the Earth-orbiting Hubble Space Telescope in the late 1990s and early 21st century captured the auroral rings around the poles. These gave vivid evidence of the high symmetry of Saturn's magnetic field and revealed details of the way the auroras respond to the solar wind and the Sun's magnetic field. Saturn's low mean density is direct evidence that its bulk composition is mostly hydrogen. Under the conditions found within the planet, hydrogen behaves as a liquid rather than gas at pressures above about 1 kilometer, corresponding to a depth of 1,000 kilometers, 600 miles below the clouds. The temperature is roughly 1000 Kelvin, 1340 degrees Fahrenheit, 730 degrees centigrade. Even as liquid, molecular hydrogen is a highly compressible material, and to achieve Saturn's mean density of 0.69 grams per cubic centimeter requires pressures above 1 megabar. This occurs at a depth of 20,000 kilometers, 12,500 miles below the clouds, or about 1/3 of the distance to the planet's center. Information about the interior structure of Saturn is obtained from studying its gravitational field, which is not spherically symmetrical. The shape of the field can be calculated from its effects on the motion of a spacecraft in the vicinity and on the shape of some components of Saturn's rings. The rapid rotation and low mean density that lead to distortion of the planet's physical shape also distort the shape of its gravitational field. Distortion is directly related to the relative mass concentrated in Saturn's central regions instead of its envelope. Analysis of the distortion shows that Saturn is substantially more centrally condensed than Jupiter, and therefore contains a significantly more considerable amount of material denser than hydrogen near its center. Saturn's central regions contain about 50% hydrogen by mass, while Jupiter's contain approximately 67% hydrogen. At a pressure of roughly 2 megabars and a temperature of about 6,000 degrees Kelvin, 10,300 degrees Fahrenheit, 5,730 degrees centigrade, the fluid molecular hydrogen is predicted to undergo a significant phase transition to a fluid metallic state, which resembles a molten alkali metal such as lithium. This transition occurs at a distance about halfway between Saturn's cloud tops and its center. Evidence from the planet's gravitational field shows that the central metallic region is considerably denser than would be the case for pure hydrogen mixed only with solar proportions of helium. Excess helium that settled from the planet's outer layers might account partly for the increased density. In addition, Saturn may contain a quantity of material denser than both hydrogen and helium, with a total mass as much as 30 times that of Earth. But its precise distribution cannot be determined from data. A rock and ice mixture of about 15 to 18 Earth masses is likely to be concentrated in a dense central core. The calculated electrical conductivity of Saturn's outer core of fluid metallic hydrogen is such that if slow circulation currents are present, as expected with the flow of heat to the surface accompanied by gravitational settling of denser components, there is a good dynamo action to generate the planet has observed magnetic field. Thus, Saturn's field is produced by the exact mechanism that produces Earth's field. See Dynamo Theory. According to the Dynamo Theory, the deep field, that part of the field in the vicinity of the dynamo region near the core, may be quite irregular. The outer part of the field that spacecraft can observe is quite regular, with a dipole axis nearly aligned with the rotation axis. Theories have been proposed that magnetic field lines are made more symmetrical to the rotational axis before they reach the surface, by passing through a non-converting electrically conducting region that is rotating concerning the field lines. The striking change observed in the magnetic field rotation period over the past 25 years mentioned above may be related to the action of deep electric currents involving the conducting core. On average, Saturn radiates about twice as much energy into space as it receives from the Sun, primarily at infrared wavelengths between 20 and 100 micrometers. Kilogram for mass, Saturn's internal energy output is like Jupiter's. This difference shows that Saturn, like Jupiter, possesses a source of internal heat. Saturn was less massive than Jupiter and had less total energy content when both planets were formed. It still radiates at Jupiter's level means that its energy is coming at least partially from a different source. A calculation of thermal evolution shows that Saturn could have originated with a score of 10 to 20 Earth masses built up from the accretion of ice-rich planetesimals. On top of this, a large amount of gaseous hydrogen and helium from the original solar nebula would have accumulated by gravitational collapse. Jupiter underwent a similar process of origin, but captured an even more tremendous amount of gas. In the capture, the gas was heated to high temperatures on both planets, several tens of thousands of kelvins. Jupiter's current internal energy output can then be understood as the slow cooling of an initially hot planet over the age of the solar system, some 4.6 billion years. If Saturn had slowly cooled, its energy output would have dropped below the observed value about 2 billion years ago. The most likely explanation for the required additional energy source is that Saturn's interior helium has been precipitating from solution in hydrogen and forming dense raindrops that fall. As the helium droplets in the metallic phase of hydrogen rain down into deeper levels, potential energy is converted into the kinetic energy of droplet motion. Friction then damps this motion and converts it into heat, which is carried up to the atmosphere by convection and radiated into space, thus prolonging Saturn's internal heat source. This process also has occurred, although to a much more limited extent, in Jupiter, which has a warmer interior and thus allows more helium to stay in solution. The Voyager's detection of a substantial depletion of helium in Saturn's atmosphere initially was taken as a vindication of this theory, but it has since been opened to question. Although Saturn's rings and moons seem to make up two groups of entirely distinct entities, they form a single complex system of objects whose structures, dynamics, and evolution are intimately linked. The orbits of the innermost known moons fall within or between the outermost rings, and new moons continue to be found embedded in the ring structure. Indeed, the ring system itself can be considered to comprise myriad tiny moons, ranging from mere dust specks to car and house-sized pieces, in their orbits around Saturn. Because of the difficulty in distinguishing between the largest ring particles and the smallest moons, determining a precise number of Saturn may
Che mamari nina. Tura la ba. Kopana lana tula ba. Lana, Che mamari nina.